I promise it's actually real this time. So the Noctua NH-D15 G2, just to clarify a few things, this is not the video from 2023. You're in the right video. Please don't click away. This is the new one. All right. So now we've cleared that up. So the Gen 2 D15 is actually happening. I have even requested a proof of life photo. And what I've been told is that such photo does exist and it will be dispatched to me post haste. And the cooler is actually in the process of shipping. So it sounds like June is, I'm getting the nod. So it sounds like June is when the D15 G2 is happening. There's a lot to talk about today. So we're gonna split this video into kind of two halves of the same video. I'm gonna focus on product stuff. I will be joined by Jacob off camera here in a little bit to talk about some of the specifics. But to get into the details straight away on the G2, there are a couple things you need to know. The first one is that this is the cooler, but we're gonna be covering some familiar details to people who saw our Coldplate and IHS flatness discussion. There's some really specific detail on fan mounting and structure as well. And then they also have a setup here just showing the original D15 that later might be running some heat loads on it. All right, the details that matter the most right away, $150. And it's going to be an expensive air cooler. A lot of that comes in from the fan. Before that, this video is brought to you by Thermal Grizzly's Aeronaut and Hydronaut thermal pastes. Aeronaut is Thermal Grizzly's entry-level thermal solution, marketed as resistant to curing and for long-term endurance. Hydronaut is Thermal Grizzly's next step up, targeted for overclocking and higher performance applications. We've used Hydronaut on a lot of our systems internally over the years. You can learn more at the link in the description below. So for the $150 kit, what they're shipping is the cooler itself, the two fans, and then this small piece of paper down here has 4 washers on it. So these are 1mm washers. It's for an ILM washer mod. We're gonna get into detail on that with some of these pressure maps too. So Noctua is at a point now where, as we've seen with air coolers in general, to further tune, to get any additional performance out of it, you have to start doing tricks that may be outside of the cooler itself. So as an example, where we see the best coolers in our testing right now, there's kind of like a 3-degree cluster of plus or minus, and they're all basically in that range if they're the best coolers. Fighting for an extra 1 to 2 degrees is very difficult at this point, and where Noctua is trying to do that with the G2 is going to be in the 3 variations. So they have an LBC or low base convexity, HPC or high base convexity, and then standard. Standard's represented by the green line over here. And one of the things we'll be going over is some of the temperature differences that Noctua is seeing based on what sort of CPU you're pairing with the Coldplate. And so the problem comes in with actually looking at flatness. Again, this is an AM5 solution. There's CPU only, this is CPU in socket, and then we've got basically the deviation in flatness. So the problem we saw with Intel was that when you clamp the ILM down, it has that really deep concavity, and that gets worse, Noctua was saying, over time, which is not an aspect that we explored in our testing. So that's incredibly interesting because it causes all kinds of new and wonderful problems for our test benches that we just deployed. So I'll get to talk about that more soon. Back to the G2 though. So other differences for the cooler include the heat pipes. They're going up to 8 heat pipes from 6. These are sintered heat pipes. They say they've done some heat pipe tuning. And in addition to that, the fin pitch and density has changed. So if you look in the side-by-sides we have of the original versus the new one, you'll see that difference in the actual fin stack. The fans are different. That's a large contributor to the performance change as well. There's the Coldplate tuning that comes from the 3 variations, depending on which you want for the convexity. And then that'll cover kind of the key differences for the G2. So we need to test it still in a fixed heat load, like for like scenario. So they've got 180 watt, 7950X, 250 watt, 13900K over here. In these scenarios, about 2 to 3 degrees different depending on what you're comparing. So I think ideally, if you're trying to be a perfect comparison, you would look at G1, of course, that's the gray line, so that's the original that everyone knows. And then standard is going to be probably the most typical or most comparable to the way that Noctua used to do it, as opposed to now where they have 3 different SKUs for the Coldplate alone. So 2 to 3 degrees at that heat load. As we always say, temperature is not a fire strike score, so it's going to change depending on what you're running. But that gives you an idea for where it falls. As for what 2 to 3 degrees means in, say, one of our benchmark charts. If it were to materialize in such a way in one of our own tests, that's the difference basically between kind of the middle of the pack, the best coolers, and the top. So it matters. It's a big difference, but we'll test that later. For a couple of other products quickly before we get into some of the engineering discussion with Jacob. So I'm not going to spend any time over here. I know Noctua cares a lot about it, but we don't do much with power supplies. So this is a Noctua Edition power supply. And we're going to breeze past that, but it's something they're working on. There's also a super prototype two-phase Thermosiphon, which you see here. So this is a pumpless in a sense. There's no mechanical moving parts to a pump for the Thermosiphon. We have covered Thermosiphons in the past. The fact that Noctua is trying something like this is honestly super cool, just because my entire experience with Noctua has been air. So it'll be something different. There's no presence on a roadmap right now. They're not making any promises for dates, no information about price. So purely from a, hey, look at the thing we're doing standpoint, the solution basically is, it looks like about a 240 standard-ish radiator with, you got 2 tubes running down, there's an evaporator, there's a condenser. As the liquid heats up, refrigerant actually, it'll evaporate, it travels through the Thermosiphon, and then will recondense. So in some ways, there's some concepts that are shared with just a heat pipe in that you have an evaporator, you have a condenser, the liquid does evaporate, does move, but the heat carrying capacity will be far greater, and what Noctua is shooting for is comparable to an AIO solution, because if you're going for liquid cooling levels of performance, but you don't want the extra physical mechanical point of failure in a pump, then there aren't many options. So Roman's shown a few in the past, for example, with his Novec fluid. That's a whole different thing. So hey, Thermosiphon was pretty cool. There's really no concrete product level detail on that for now. The last thing on Noctua's tail before we move into the engineering is just some server side stuff. So over here, for example, there is a Grace Hopper cooler. We just saw some Blackwell servers with Grace in them in one of our other videos. And otherwise, there's a 120 millimeter fan that is also in the Gen 2 lineup. So this, it doesn't have a name. So this is the NF-A14 Gen 2, G2. This is unnamed, but otherwise like a smaller version of the NF-A14 G2. You might say it's a NF-A12 G2. If I were to pick a name, you can have that one for free. I've coined it right here. That's my name of the product, whether Noctua uses it or not. All right, let's jump over to some engineering discussion. Now we are joined by Jacob for the engineering part of the discussion. Jacob and I spoke last year at this booth and had an awesome engineering topic. We actually have more coming up after the show. There was something you wanted to clear up, though.
Yeah, absolutely. You mentioned that you want to see that photo of the D15 G2 coolers being packed. I took this one yesterday at our factory. You can see it. I zoom in a little bit so that you can count the heat pipe number.
1, 2, 3, 4, 5, 6, 7, 8. It is the D15 G2.
They are being produced as we speak, being packed, being shipped to warehouses around the world. And yeah, we aim to have them available on the market by end of June.
So it's happening. So we have some really cool engineering topics that we'll get into kind of at least overview here. So the fan is one where you were talking about these, there's this little rubber bump here, and that actually ends up being something somewhat significant. So we're going to talk about that. And then we've also got the Coldplate curvature. Where do you want to start?
Let's talk about the fans first, okay. Because this is something we've discussed at length at last year's Computex. Back then, our plan was to use LCP not only for the impeller but also for the frame to further strengthen it, to avoid that deformation we saw when using the fans on water cooling radiators, but also with heatsink fan clips. Sadly, the long-term tests we've been running back then didn't show the desired results. So even the stronger LCP over longer periods of time will eventually have those deformation issues. It's basically just shifting the point of time where we come into critical territory. It's basically whenever you have a plastic part bolted to a metal part, eventually even the hardest plastic will give in. Yeah, this is why the targeted start of production date of end of last year didn't hold, and why we're still not having the fan out on the market. However, we have done some adjustments on the fan frame as such. We've strengthened the structure of the fan frame as such, and at the same time reduced the amount of force that goes into the fan. And these little silicone pads are part of the story. You can see those little rings around the mounting holes. We call them load relief rings. And what they do is that they distribute the counter pressure the fan gets when it's bolted down onto a radiator more evenly. So without those load relief pads, we have compressive force from the screw going down onto the fan, and counter pressure from the radiator just at the very edge of the frame. And this enables the part around the mounting hole to go further down, and torsional warp being introduced into the frame. And that torsional warp is causing the long-term deformation we've been battling with for so long.
So how much of this is a performance? Is it all performance oriented? You're trying to prevent performance problems by having gaps? Is it structural? Is it, what are the key parts of it?
I mean, I would say it goes hand in hand. We need that super tight tip clearance to achieve the desired performance levels, so we don't want to compromise on that. But it's basically a lifetime issue, lifespan issue that requires us to avoid the deformation. Because if you would have a fan running for, let's say, 6-8 years at relatively high temperatures, this is where you could run into that type of issue. And this is where the new load relief pads and the strengthened frame step in to prevent that type of issue, because we want our fans to run for at least a decade or even longer if possible. One thing to keep in mind with this is that we still don't want you to torque the fans excessively. We advocate 0.2 Newton meter maximum torque, which may sound like very low torque to apply, but with your average radiator screw, that will amount to a total compressive load on the entire fan of around 30 kilograms. So it's not like the fan is fragile, it's it's quite easy to apply a lot of force with screws, especially because some of the screw heads are very small, so you have very little friction between the screw head and the fan frame. Also, sometimes lubricants are used to prevent the black paint from wearing too quickly, and those lubricants also reduce the friction between the screw head and the fan frame.
Was there anything else, in this topic you want to go over before moving over to the IHS stuff?
Yeah, I mean, one thing we could explain as well is timelines, and why the timelines differ for the round frame and for the square frame. In both cases, we initially targeted using LCP for the frame. And in both cases, we ended up, thankfully, getting away with just structurally modifying the frame to be stronger and reducing the amount of force that goes into the frame when mounting. So in both cases, we could now stick to ABS PBT, which enables us to stay at the €40 USD price point rather than going even higher, which would have been necessary if we used LCP. The modification we had to do on the round frame was slightly smaller than what we had to do on the square frame to make it work. And this is why the round frame fan is coming with the cooler end of June, and the square frame is going to come in September. One more note on the square frame, that is for the beige and brown version. Black version, we know people want it, it's in the works, current target is Q1. But we've talked at length last year about how difficult it is to create injection molding toolings and to validate that everything is working perfect. So before we want to get going with the black one, we need to make sure that the regular one is going okay, and then we'll do our best to get the black one out for people as quickly as we can.
And I forgot to say this in the first part, but it's already publicly known the white fan is just kind of on hold right now with no target date. So so these are the two that you guys are working on. With this one, immediate future.
Yep.
Anything else here before moving over?
I mean, we could talk a little bit about what sort of performance metrics to expect. Will it be worth the upgrade over the existing A14? We've got some performance data here. Noise normalized results on a water cooling radiator. We're seeing roughly a 3-degree improvement, which is massive. We have a little bit less when the resistance is slightly lower, like on a heatsink, but this is still more than 2-degree improvement in the benchmark we're showing here. One little explainer before people complain about the graphs. Some people may notice that the temperatures are very similar for the 200 watt results on the water cooling radiator and the 320 watt results for the cooler. The reason is that we used a hotspot centered heating element for the water cooling tests and a uniform heating element for the cooler tests, and that's why the delta temperatures are similar despite the different heat loads.
It's like watching I feel like you would do very well running a hardware review YouTube channel, because you're already caveating everything, which is what I have to do.
I know that comment would come, and it's a valid point to make. I mean, if I was looking at that data, I would say, hey, there's something wrong here. And yeah, there's something wrong. We forgot to add that the one test was hotspot and the other one was uniform.
But the data's fine, it's just the nomenclature. So let's move over here. So quick primer, we have a video on the channel for those of you who haven't seen it. It gets you some laser scans and looking at IHS, Curvature, and especially Intel with the ILM. So by pure coincidence, we were both putting together some presentation at the same time. Probably you've been running the test a little longer. But we had some similar conclusions. One of the comments I made in that video was, you know, for a manufacturer to really take advantage of this, they'd have to make multiple SKUs of the same thing, which is what you guys are doing, and why it was so awesome that coincidence lined up, because I'm actually primed to talk about this. I think I want to, since you gave me the run through, I'll just define kind of the grid we have, and then I'll let you take it away.
Sure.
All right, so key points to look at when Vitaly shows the footage on the screen. There's this block over here where the heatsink is illustrated with its curvature for over here, the basically axis label, if you want to look at it that way. Then there's CPU. They have the CCD presence for AMD, and then it's the different, so the HBC, LBC, and standard. There's some thermal numbers at the bottom. Up top, there's the actual deviation that we'll talk about. And then there's also offset mounting. So basically, if you look at it like a matrix, it's standard mounting, offset mounting, HBC standard, LBC, and then the presence of, or the actual CPU heatsink curvature. Let's run through, I want to just start with this gigantic deviation we're seeing here, and I'll let you explain it.
Yeah. So I think it's become quite common knowledge. You've shown it again in your recent video that Intel LGA 1700 CPUs deform heavily under ILM pressure. So once you close the internal loading mechanism, you have those two tabs pressing down on the side of the integrated heat spreader, and that will cause it to warp quite heavily. It's actually a complex warp, so you're seeing a slight convexity in east to west direction, but that's very slight, but you're seeing a huge concavity in north to south direction, and that's what really impacts cooler contact quality. Now, the interesting thing is that when you take a factory new Intel CPU, scan it, it's actually gonna be convex. So we're north to south, that is. We're talking about something like around 15 micron range convexity. And the first time you put it into the socket and close the ILM, it will go to concave around 25 to 35 microns. Yeah, it's important to keep in mind that the deformation we see is partly plastic, partly elastic. So when you take the CPU out of the socket, it will go back, but it will not go back all the way. And then will depend on multiple factors, like how much pressure your ILM actually applied, there are tolerances to that, how much high heat load testing you did, how long you had it in the socket. So one thing we definitely see is increasing deformation over time. So it's not like you close the ILM for the first time and that's it, but the deformation will progress. And progress to different levels depending on the parameters I've already mentioned. Heatsink mounting pressure is also a parameter that comes into play. The bottom line is that we have seen CPUs that go up to around 55 micron concavity, and that means that if you put a flat heatsink on that CPU, you will have basically no contact whatsoever over the die.
It's like a lake, you know, like it's basically forming a lake. So.
The key problem is that it introduces a lot of complexity, not only for customers but also for heatsink reviewers, because it means that the results may look different between what you're getting on a fresh CPU and what you're getting, I don't know, let's say 3 months down the line, if the CPU has been used heavily for cooler testing, just because it has deformed a lot, and the contact situation for each heatsink has changed.
Now, how about for that specific comment? How about for AMD? What's your observation been there?
Well, the AMD IHS is much thicker, and this is why we see much less deformation for AM5. When you look at the pure numbers alone, it's actually not so dissimilar to what we see from Intel if you do the washer mod. We're going to come to that in a minute, I guess, or using contact frames. But when you look at the surface scan we have up there, you can see that the deformation we get on AM5 is actually very limited to the areas where the socket actuation mechanism presses onto the heat spreader, and the main contact area for the heatsink is staying relatively flat. And this is why we generally see very good results with relatively flat heatsinks on AMD.
So and then there's these, we call them pseudo color in our lab, but these pressure scans, I guess. Well, is it a pressure scan, or are you trying to show a hot spot here? Pressure?
This is a pressure scan.
Okay.
This is purely pressure.
So pressure scans, walk me through some of these for the different SKUs.
Yeah. So maybe we should start with AMD first, because it's perhaps a little bit easier. We have you already mentioned the HBC, the high base convexity version, the standard regular version that has the same medium base convexity like all our other multi-socket coolers do as well, and the low base convexity LBC version. And when you look at the pressure scans, you can see that the HBC version has a very concentrated pressure pattern on AM5, and it's like straight on the IO die without the offset mounting, and shifted towards the CCDs with the offset mounting, but still the contact area is relatively small. And if you move on to the regular version, you can see a slightly bigger contact patch that's nicely spreading across the CCDs with the offset mounting, and that's why we see excellent results with the regular version on AMD once you use the offset. In case, however, you don't want to use that offset mounting, the LBC version is going to give you excellent contact quality even without the offset. So you can see that it's got very nice contact both over the CCDs and over the IO die. So if you want to have the best temperatures on both the CCDs and the IO die, the LBC version is what you want to get.
So we should probably, I didn't talk about this in the first part of the video, I probably should have. So for addressing confusion, right? I asked you, what are the reasons you wouldn't just always do this? Some of them are kind of obvious in terms of making 3 different variations. Some are obvious. The biggest one is definitely customer knowledge. So we should briefly go over that just as simply as possible. How does Noctua see each of these 3 most optimally being deployed?
Precisely. I mean, that's why I was so happy when I saw your video coming out, because customer education is going to be key here. I think the first and perhaps most important message is to get out is you cannot really go wrong with the standard version. The standard version is the best all-rounder by far. It's going to give you the best possible results on AM5 with the offset mounting, and we're including shim washers to reduce ILM pressure on Intel LGA 1700. And this way it's going to give you the best possible results on a fresh Intel 1700 CPU as well. The only case where the standard version is going to lag behind a little bit is if your Intel CPU has already been in use and has been heavily used so that it has become heavily deformed. This is when you definitely want to go with the HBC version. So I think for customers who feel confused about this or say, oh, I just don't want to bother with all that, just go for the standard version. You're going to be happy with it. But it's really those customers who know their exact use case and they want to edge out that extra 1 or 2 degrees. that's where you might want to go with the LBC or HBC version.
I guess an example too is like lapping or something where the LBC, if I understand it right, if you were to lap your CPU, that would get you the closest to flat, I guess, of the three.
I mean, lapping is a tricky business. You would have to know what you do, and you would probably have to lap it in socket to actually get it flat in socket. Otherwise, you may end up with weird results.
So this is where we have to assume a spherical cow again. I was afraid to bring up lapping because I was thinking like through variables as well. But yes, no, I agree.
Sadly, it's not as straightforward as it seems. But there are also custom heat spreaders, so you could replace your heat spreader with a custom one that should be actually flat because it's properly made, hopefully, by a CNC machine. And that's definitely a case where you would want to go with an LBC cooler. Another case would be if you're running legacy sockets, like if you're still on an LGA 2066, on AM4, on 2011, or if you just for some reason don't want to use the offset mounting we offer, then the LBC is going to be a great option for you.
Is there anything you want to go over on the Intel side over here? So
yeah, I mean Intel, it's basically the other way around. So if we start with the LBC again, we see that with full ILM pressure, there's hardly any contact in the critical die area. If you use the 1mm washers we supply, you're actually starting to get decent contact even with the low base convexity version. And if we move up to the standard middle base convexity version, you can see that with the washers on a fresh or relatively fresh CPUs, you're getting the perfect, nice concentrated contact you want to have exactly over your die. You can also see that the standard version without washers is lacking a little bit of contact in the central area. So it's not the end of the world, it's going to do okay, but there's room for improvement. So if you don't want to use those washers or a contact frame, for example, then you would want to go for the HBC version that has excellent contact, even if you don't use the washers. On a fresh CPU, if you put in the washers with HBC, you're actually ending up with a little bit too concentrated pressure. But if you have a really heavily deformed CPU, like we've had some that were used for heatsink testing for months, then actually combining HBC with the washers can give you the best results. So yeah, I understand it's a complicated story to tell, but sadly the situation is complicated. So I'm afraid it doesn't get much more straightforward than that.
And also, I mean, frankly, so it's a complicated story to tell in the testing, of course, but ultimately we'll look at all this in our benchmarking and probably do like a matrix. I guess we'll end up with like a 9-test matrix or something, but
it's going to be a big graph.
Yeah. So ultimately from someone building a computer perspective, hopefully, as reviewers, our job is to just give the answer as much as we can. So it should simplify it a bit if this is overwhelming. I don't think it'll be necessary for people to necessarily have a full comprehension of all this, which we'll talk about in the review. So, Jacob, why don't you just make something easier? Have you ever thought about, so you're talking about like how different color fans is different difficulties. Do you ever think about just not caring? Put some LEDs in it, maybe $9.99. Maybe it moves air, maybe it doesn't. What do you think?
I guess it's just not our cup of tea, sorry. I mean, for this one, honestly, we were debating if we should go for the 3 different SKUs because it's difficult from a customer education perspective. It's more difficult at least from an economy of scale perspective. It requires very tight tolerance control in manufacturing, but we do have that anyway. We did control base convexity with every heatsink that leaves the factory anyway, so that is doable for us. And then in the end, what we want to do is offer the best possible solution for our target audience. Our target audience is caring about performance first and foremost, and that's what we're going for.
So check back for the review and for more discussions with Jacob. We have a couple engineering videos we already shot. They'll be up after the show. And thank you again for joining me.
My pleasure. Thank you very much for coming.
Absolutely. And we'll see you all next time.